Now, if we notice for the comparator, most of the time the output is saturated, right? Not? Now, saturated output is not necessarily bad because in a comparator, we just want the output to be either positive or negative, which is sufficient for us to turn on and off a relay or turn on and off an LED lah. But if you want to use an op-amp without saturation, you have to use a process called negative feedback. So what is negative feedback? Negative feedback by definition is the process of taking some or all of the output of the amplifier and adding it to the input. And then you must add another sentence. Can you copy another sentence below this? The output must be 180 degrees. The output must be 180 degrees out of phase with the input. The output must be 180 degrees out of phase with the input. So in the diagram, what it looks like is you take some of the output, you feed it back to the input, and then you get a new gain. Alright, now I'll show you another diagram how it looks like. So if you look at this diagram, it gives you a better illustration of what they are trying to say about negative feedback. You see, normally our very small input will produce a very large output because remember your gain is very high. So what they do in negative feedback is they take a portion of the output. Can you see your output is 180 degrees out of phase with the input? Can you see it's 180 degrees out of phase? So I take a little bit of this, which is here. That means I take a fraction of this output, which is this. I add it back to the same input as this. So I take a fraction, which is this. I add it back to the same input. Now when I add together, wouldn't it get smaller now? So therefore, a smaller input will produce a smaller output. So that's what they're trying to say only lah. Okay, but later on when we look at the circuit it's a bit different but it's just an idea what the definition means lah. Now then the question is, what are the benefits of negative feedback? I mean, obviously one is to reduce your gain so that you won't saturate, but what are the 3 benefits of negative feedback that you need to write down? So the first one, they said the first benefit is an increase in the range of frequencies over which the gain is constant, which means to say increased bandwidth. Now what does it mean by increased bandwidth? Now remember our graph of gain versus frequency is given by this graph, right? Okay, so gain versus frequency. So what will happen is, initially without negative feedback, your bandwidth is here. That means your bandwidth is the maximum frequency where your gain is constant, and it is constant. There's a straight line here up to 7 Hz. So without negative feedback, your bandwidth is only 7 Hz. But if you somehow can reduce your gain to, let's say, 10 to the power 3, if you reduce your gain to 10 to the power 3, then the new graph will be this. So when your new graph is this, that means your new bandwidth is now 1000 Hz. So that means if you are using an AC input, you can go up to 1000 Hz and your gain is still constant at 1000. If any frequency more than 1000 Hz, then only it will drop. Without negative feedback, you only have a constant gain for 7 Hz. After that, you start to drop only. Now, if you increase if you reduce the gain even further, you will increase the bandwidth even further. So if let's say you reduce the gain to only 10, then this is your new graph. Alright, so I use a different color. So this is your new graph. So which means to say the top doesn't exist anymore. So that means you get a constant gain up to 10 to the power 5 Hz. So your bandwidth is higher. So then people say, so what is the good thing about having a larger bandwidth? So it's also related to the next part, which is less distortion. So what does it mean by less distortion? Now assuming your input voltage, alright, this is your V in, is a very small voltage. Now if you don't have negative feedback, so without negative feedback, how will your graph look like? Wouldn't it be a very big gain? So you can imagine it amplifies a lot. Agree or not? That's why it gives you a very high chance of saturation. But then, what if we are talking about what about if we talk about waves that have multiple frequencies? Let's say it's low frequency and high frequency. Okay, let's say got low frequency and high frequency. So without negative feedback, your bandwidth will be smaller. So let's say this is 7 Hertz. This is 1000 Hertz. Okay, so when the frequency is 7 Hertz, from the original graph of this, without negative feedback, you refer to the original graph. Without negative feedback, then when your frequency is 7 Hertz, what is your gain? 10 to the power 5 right now. So this part will be amplified very big. But when your signal goes to 1000 Hertz, it follows this graph. So 1000 Hertz, what's your gain? So 1000 Hertz, what's your gain? 1000 only, right? So instead of amplifying by 10 to the power 5, now you amplify by 1000. So the second part will be smaller. Like this. Can you see there's a distortion of the shape of the signal now? But if let's say you had negative feedback, so now with negative feedback, and let's say we manage to reduce the gain to 1000. So we're following this red curve. Let's say we're following this red curve. So at 7 Hertz, it is also amplified by 1000. At 1000 Hertz, is also amplified by 1000. Can you see that? So, which means to say the entire graph here will be amplified by the same amount, which is 1000. Correct enough? So you will get, let's say this is your halfway one. So this one will be smaller, but this one also will be smaller, but at least there's no distortion. Can you see that? So basically, this one, if you without negative feedback, it will be amplified more than this part. But with negative feedback, you have a chance to have all the same gain. So in that case, you have less distortion. Okay? Now, another one is greater operating stability. So this greater operating stability, you will see in our next slide where I derive for you the equation. Now, normally, the gain of an op-amp depends, follows this graph, but it also depends on all the components within your op-amp. If any one of it heats up or not functioning well, then your graph will get distorted. But with negative feedback, you will notice that your gain only depends on your ratio of your resistances that you're going to use outside, external resistors. So in that sense, you're going to give you greater operating stability. You don't have to worry what happens within your op-amp. You just have to make sure that the two resistors you're using outside is working okay, then it's fine. But I'll come to that in a short while. So I will move on to the next slide. Okay, so now let's look at how an example of negative feedback looks like, right? So there are two types of circuits that incorporate negative feedback. One is called an inverting amplifier, which is what you're going to see here. This is called an inverting amplifier. And another one will be called the non-inverting amplifier, which will be seen in the later part, not here. So we'll talk about inverting amplifier first. So why is this called an inverting amplifier? Okay, let me explain to you that because this is negative feedback, you will see a common characteristics for all negative feedback. So negative feedback, you will have two resistors here. Well, one resistor here connecting from your output to the negative input. That's why it's called a negative feedback. So whenever you see an output connected to the negative input via a feedback resistor, it's called negative feedback. But for inverting amplifier, you have another resistor on this side, which is the Rin, which is the resistance that connects your inverting input to whatever voltage that you want to supply here. And your non-inverting input will be earthed. So you will see that this is different from a comparator. A comparator won't have this, right? Not? It's called open loop because whatever input, output, that's it, end of story. But now, this inverting amplifier is negative feedback, so it brings it back here. So this is one difference between comparator and inverting amplifier. Another difference is an inverting amplifier, this one is always earthed, the non-inverting input. So how does this reduce your gain? Okay, I'll give an example. Now let's say we start off without any negative feedback, without a feedback resistor. Let's say we start off without a feedback resistor, then it's like a comparator, right? So you'll be V out equals to 10 to the power 5 if it's DC. Your V plus is how much? Can you see it is earthed? So it's 0 minus your V in, right? So if let's say your V in is 5 volts, then your V out will be negative also, right? will be 0 minus 5, which is negative saturated lah. And you will get a negative output because this is called inverting amplifier. So which means to say, when we put in a positive value, your output will be negative. That's why it's called an inverting amplifier. But if you give it a negative 5 here, and you take 0 minus negative 5, do you realize you get positive? So that's why it's called an inverting amplifier. Because you only feed the input to the inverting side. But how do we reduce the gain? It is because of the feedback resistor. So I'm going to show you. So with this feedback resistor now, okay, let's say we have this feedback resistor, then current can now flow from here to here or here to here. Right? Agree? So since when you put in a positive, you get a negative output, current will now flow from positive to negative. Without this feedback resistor, current cannot flow because there's infinite input impedance here, remember? With this feedback resistor, current can flow across your feedback resistor. If this is negative, this is positive, then you'll flow the other side. If this is positive, this is negative, it flows this side. Can you see that? So when it flows, what happens? Now, if this is 5 volts here, and it flows across a resistor, wouldn't there be a PD? So when there's a PD, the potential here will be lower than here. Let's say the potential drops to 1 volt. And if we were to substitute into this equation, let's say we wanted to substitute this into this equation, so your V out will be 10 to the power 5, 0 minus 1, instead of 0 minus 5, right? So can you see you're going to get a smaller output? So that is what it means by negative feedback. So it makes your input smaller here. Instead of 5, now it's smaller. So now your output is also smaller. Understand that? So the bad news is you have to know how to derive this equation. The equation for this op-amp. For a comparator, we must use this on it. But this is an inverting amplifier, so we cannot use this. We have to modify this equation by actually we have to derive a whole brand new equation. So let's look at how to derive the equation. Now, to derive the equation for an inverting amplifier, so we're going to assume that you're going to give it a positive input, and so it will come out with a negative output. So how will current flow? From here to here and back to the output, right? So let's say the current here is called I in, and this current is called IF. Now, if the current cannot split because there's infinite input impedance, it cannot flow in. So do you agree the current here must be equals to current here? Or I in equals to IF? Do you agree? Okay. So I shift it a bit higher. So you start off by writing I in equals to IF. Alright, then I'm going to introduce to you a concept called virtual earth. So what is virtual earth? Since your non-inverting input is 0 volts because it is earthed, and if you don't want the op-amp to saturate, remember the two inputs must be very similar because your gain is very big. So if you don't want the op-amp to saturate, these two must be almost the same potential. So since this is 0 volts, point P must also be almost 0 volts if you don't want it to saturate, right now. So therefore, we call this point P, virtual earth. That means we assume that it is almost 0 volts in order for the op-amp not to saturate. Alright, so we talk about point P is called virtual earth. So for the derivation, you're going to assume point P is 0 volts. Alright, so since the current flows from here to here, so let's talk about the current here. What's the formula for current? Isn't it PD over resistance? Now what is the PD? You will take this potential minus P, that means V in minus P, or P minus V in. You need to see which potential is higher. If the current flows from here to here, the V in must be higher potential than P, right? So therefore the PD will be V in minus the potential at P, which is virtual earth, so is 0, over the R in. Then we do the next part, RF here. The current here is flowing from here to here, or from P to V out. So which potential is higher? Your virtual earth or V out? Virtual earth. So 0 minus V out over RF. So then we group the V out over V in to one side. Then you get negative RF over R in. And can you remember for an op-amp, V out over V in is also the formula or the definition of gain. So now your gain is basically just the ratio of two resistance, RF over Rin. You want whatever gain, you just play around with these two resistance. You want your gain to be 10, 10 ohm, 1 ohm. Or 100 ohm, 10 ohm. Or 1000 ohm, 100 ohm. Up to you. If you want your gain to be 100, then it will be 101. Understand? So in that case, you get fixed whatever gain you want. And can you see there is greater operating stability? Because now your gain only depends on this. It doesn't bother about the condition of your op-amp inside there. Understand? Okay, so remember, if it's inverting amplifier, you can only use this. Okay, so let's do some questions.